We often just sort of accept time, don't we? It's always there, ticking away.
Yeah, it's the ultimate background process.
But when you actually stop and think about it, it gets seriously mind-bending.
Mhm.
There was this recent conference, FQXI's Setting Time All Right. Sounded amazing.
Oh, yeah, I saw some posts about that, like a cruise ship full of scientists and philosophers arguing about time.
Exactly. A cruise from Bergen to Copenhagen, physicists, cosmologists, philosophers, biologists, psychologists, and get this, even a quantum complexity blogger.
Wow.
All debating, does time exist? Which way does it point? What is it? Fundamentally, super cool.
Definitely. And Sean Carroll was there, right? He writes great stuff.
He was. And a question he posed really stuck with us.
Okay. Oh, was it?
He asked why the complexity, or maybe interestingness is a better word of things, seemed to increase, then peak, and then fade away.
Well, entropy just keeps going up.
Right.
Yeah.
Entropy, disorder, it just increases relentlessly. But the interesting stuff, the intricate structures, they seem to have this arc.
Why? That is a fundamental head scratcher. You start simple, things get fascinatingly complicated, and then it all just kind of dissolves into blandness eventually.
Exactly. So that puzzle is what we want to tackle in this deep dive.
Okay.
We're going to explore a potential answer, and it involves some pretty neat ideas from something called Kolmogorov complexity.
Ah, Kolmogorov. Okay, yeah, this should be interesting.
So yeah, get ready. We're diving into entropy, this idea of, let's call it complextropy, maybe, to keep it clear.
Complextropy. I like it. Avoids confusion.
Right. And how Kolmogorov complexity just might, give us a framework to understand this whole thing.
Sounds good. So, starting point. The second law of thermodynamics, entropy.
Right. The basics.
Mm.
In a closed system, entropy, randomness, disorder, whatever you want to call it, tends to increase. Heads towards a maximum.
And, as they probably discussed endlessly on that cruise, defining entropy perfectly is tricky.
Oh, for sure. It's slippery.
But the core idea holds. Things tend to get more disordered over time.
Which, of course, brings up that other massive question. Why was the universe's entropy so incredibly low to begin with?
Yeah, the ultimate why. That low starting point is what allowed everything interesting to happen.
We're not going to solve that one today, obviously.
No, probably not. But it's crucial background.
Definitely. Because entropy just goes up monotonically, but complexity or complextropy doesn't.
Mm.
Sean Carroll's coffee cup example is perfect here.
Right, the coffee and milk. You start with them separate. That's pretty ordered, low entropy, simple.
Then you stir.
And you get those fantastic, intricate swirls and tendrils. What's really complex, right? Very interesting visually.
But the entropy is also increasing as they mix.
Exactly. And then eventually...
It all just becomes a uniform light brown, maximum entropy for that mixture. But, well, it's boring again. Simple.
Precisely. Less complex than that middle swirly stage.
And you see this on the grand scale too, right?
Yeah.
Early universe. Simple, hot, dense soup. Low entropy.
Relatively speaking, yeah.
Today, galaxies, stars, planets, us. Unbelievably complex structures. Higher entropy overall, but wow, the complexity.
And the far, far future.
After black holes evaporate, everything cools down. Just a thin, cold, uniform soup of particles again. Maximum entropy. Very simple.
So complextropy seems to rise and fall, a peak somewhere in the middle of cosmic time.
Which gets us back to Sean's question and the challenge. It's sort of twofold, isn't it?
Yeah, the source material lays it out clearly. First, you need a good formal definition. What is this complextropy we're trying to measure? What counts as interesting?
That alone sounds hard.
It is. And second, even if you have a definition, you need to show that it actually does peak at intermediate times and, reasonable models of how things evolve.
Okay. It feels intuitive that complexity would be low at the start. Low entropy kind of puts a cap on it, maybe.
Plausibly, yeah. Low entropy states are often simple states.
And at the end, everything's in equilibrium.
Yeah.
A uniform distribution.
Mm-hmm.
That feels simple too.
Right. Maximum entropy states often look like random noise, basically featureless.
So the real mystery is the middle. Why does it get so complex in between those two simple ends? How does that happen?
And this is where Kolmogorov complexity might offer some traction.
Okay, so Kolmogorov complexity, what's the core idea?
It's about description length. The Kolmogorov complexity of a string of data, like a sequence of bits, is the length of the shortest possible computer program that can print out that exact string and then halt.
Shortest program. Okay, so a string like 010101 repeated a million times has low complexity.
Very low. The program is basically print il1 a million times. Short program.
But a truly random string of a million bits.
That would likely have very high Kolmogorov complexity. Because there's no pattern to exploit, the shortest program is probably just print this specific sequence,
Yeah.
followed by the million bits themselves. The program is almost as long as the string.
I see. It's about compressibility, in a way.
Exactly. Highly compressible means low Kolmogorov complexity. Incompressible, random-looking stuff has high complexity.
So people tried to use this to define entropy.
They did. But there's a catch, especially with deterministic systems. Like, imagine your grid of cells evolving according to fixed rules.
Okay.
To describe the state after, say, T steps, what do you need? You just need the initial state, which is some fixed number of bits, let's call it C.
Right.
And you need the number of steps, T, how many bits to specify T. Roughly log base 2 of T.
Okay.
So the total information, the Kolmogorov complexity of the state at time t, is basically just C plus log t. It only grows logarithmically with time.
Logarithmically. That's pretty slow growth.
Much slower than how we usually think entropy increases in physical systems, which is often more like linear or polynomial growth. So simple Kolmogorov complexity doesn't quite capture entropy's behavior in these cases.
Huh. So that initial idea didn't quite work out.
Not directly for entropy and deterministic systems. There are a couple of ways around this, though.
Like what?
Well, one is to consider probabilistic systems. If the rules have some randomness baked in, then the Kolmogorov complexity of the state can grow polynomially faster. That aligns better with entropy.
Adding randomness helps. What's the other way?
The other involves resource bounds. Thinking about resource-bounded Kolmogorov complexity.
Resource-bounded, meaning?
Meaning you don't just care about the absolute shortest program in theory, but you also care about how much time or memory that program needs to run.
Practical limits.
Exactly. Maybe there's a tiny program that could generate the state after a billion years, but if you only have, say, polynomial time allowed, the shortest program that works within that time limit might be much longer.
Okay, so putting limits on the computer running the program.
Right. And if you do that, you can also get complexity measures that increase polynomially, more like entropy.
Interesting. So that helps align complexity with entropy. Well, what about Sean's question? The rise and fall of interestingness, or complextropy.
Right, back to complextropy. Standard Kolmogorov complexity, even resource-bounded, doesn't automatically give you that rise and fall. A random string has high Kolmogorov complexity, but it's not interesting in the way we mean.
It's just Emma noise.
Exactly. This is where another idea from Kolmogorov complexity comes in, called sophistication. Apparently, Kolmogorov himself thought about this back in the 70s.
Sophistication.
Yeah. The intuition is just what you said. A truly random string is maximally complex by the basic Kolmogorov measure, but it feels simple. It lacks structure. The best way to describe it is just, it's random.
Like white noise on a TV. High entropy, high Kolmogorov complexity maybe, but not sophisticated.
Precisely. And a very simple string, like all zeros, also isn't sophisticated. Sophistication is meant to capture that middle ground, something that has structure but isn't trivially simple or perfectly random.
How do they define that formally? Sounds tricky.
It is a bit subtle. It involves thinking about sets of strings. For our string x, we look for a set S that contains x. This set S should be describable by a relatively short program, low kx.
Okay, a simple set.
And crucially, within that simple set S, our string x should be essentially random or typical, meaning the extra information needed to specify x, once you know the set S, that's kx, should be close to the maximum possible, which is about log base 2 of the number of strings in S.
Let me try to unpack that. So if x is simple, like 0, 0, 0.
Then the simplest set S is just small. Kx is basically 0 because once you know the set is just 0, 0, 0, x, so low sophistication.
And if x is a truly random string of length n?
The simplest set S containing it is probably the set of all strings of length n. Ks is small, program, generate all n-bit strings, and x is a typical member, so kxs is large, close to log base 2 of s, which is n. But the sophistication is defined as the ks part, the complexity of the set's description. So random strings also have low sophistication because the set they belong to, all n-bit strings, is simple to describe.
So sophistication is the complexity of the model or structure, the set S, not the complexity of the random bits within that structure.
You got it. It captures the complexity of the underlying pattern or ensemble from which the string looks like a typical draw. And a guy named Alexander Shen actually proved that strings with high sophistication do exist. It wasn't obvious they had to.
Okay, so sophistication seems promising for capturing interesting structure. Does it explain the rise and fall?
Unfortunately, not quite, at least not in its standard form. Just like basic Kolmogorov complexity, standard sophistication also tends to grow slowly, like log E for deterministic systems.
It's all too slow.
Yeah, and even for probabilistic systems, if they just settle into a uniform random state over some set hoc, the sophistication tends to be low again because the set itself is simple, uniform over these states.
So still missing that peak in the middle. What's the next step then? The proposed fix.
It seems the key is to combine sophistication with those resource bounds we talked about earlier.
Ah, putting it all together.
Yeah. Define complexropay using resource-bounded sophistication. So we're looking for the length of the shortest program that runs within some time limit, maybe n log n or something polynomial.
Okay, efficient program.
And this program should output samples that are almost uniformly random from some set S.
Right.
And here's the kicker. Any other program running within the same time limit, if you give it access to samples from S, it still needs a lot of information, roughly log base 2 of S bits, to figure out our specific state X.
Whoa, okay. So the set S itself must be generatable efficiently.
Yes, you need to be able to produce typical members quickly.
But pinpointing the actual state X within that set, even with examples, has to remain computationally hard within that time limit.
Exactly. It's like the overall structure S is somewhat simple to grasp or simulate, but the specific details X are hard to reconstruct quickly just from knowing the structure.
That feels much closer to the coffee cup swirls. You can sort of see it's mixed coffee and milk. But describing that specific swirl pattern precisely is really hard.
That's the intuition. And the source material really emphasizes that these computational efficiency bounds on generating the set and on reconstructing a specific element are absolutely crucial. Without them, this measure probably wouldn't show the rise and fall.
And the big idea, the conjecture is,
The conjecture is that this measure, this resource-bounded complextropy, will exhibit what the author cheekily calls the first law of complexodynamics.
I like that.
It states that this complextropy will be low initially, simple state, high at intermediate times, complex structured state that's hard to pin down quickly, and then low again at the end. Equilibrium, simple random state.
That really could be it. That feels like it captures the phenomenon.
It's a compelling hypothesis.
But as the author admits, proving it, that sounds incredibly difficult.
Oh, yeah. Proving things about Kolmogorov complexity, especially resource-bounded versions, is notoriously hard. It borders on logic and the foundations of computation.
So what are the practical next steps? How do you even test this?
Well, the first thing is to make it concrete. Choose a specific model system, like that discrete coffee cup.
The grid of black and white pixels swapping places.
Exactly. Define the rules, define the resource constraints, like the time limit for programs. Then you can try to analyze it.
And the intuition there is.
The intuition is start, simple description, half black, half white, end, simple description, random gray noise, middle. You have these incredibly complex fractal-like boundaries between black and white regions.
Describing those boundaries efficiently might be the hard part.
Or generating a typical state with such complex boundaries quickly might be hard. That's where the resource-bounded sophistication might peak.
You could try to prove it for that model.
You could try. But, as mentioned, proofs are tough. The other approach is empirical, simulate it.
Run the coffee cup simulation on a computer and try to measure this complextropy over time.
Yeah. Now, actually, calculating resource-bounded sophistication is also incredibly hard, probably impossible in general.
So how do you measure it in a simulation?
You use proxies. A common trick in this field is to use data compression algorithms like gzip or bzip2.
How does that help?
The idea is that highly structured, non-random data, low complextropy maybe, compresses well. Highly random data, also low complextropy, also compresses poorly because it's random. But maybe that intermediate interesting state with complex structures compresses least effectively.
Because the patterns are too complex for a simple compressor to find quickly.
Something like that. It's a heuristic, definitely not a perfect measure of Kolmogorov complexity or sophistication, but it's something you can actually compute. You run the simulation, take snapshots of the state at different times, compress each snapshot, and see if the compressed file size shows that rise and fall pattern.
That's clever, pragmatic.
And apparently this isn't just theoretical. The source mentions an MIT undergraduate, Lauren Ouellette, is actually doing this, trying to empirically test these ideas using the coffee cup model.
Wow, really? That's fantastic. So people are actively working on simulating this first law of complexodynamics.
Seems like it. It's very much ongoing research, trying to see if this computationally grounded definition of complexity matches our intuition and Sean Carroll's observation.
Okay, so let's try and wrap this up. The big picture is we have this puzzle. Why does interestingness peak while disorder just increases?
Right. Entropy goes up, complexity goes up, then down.
And the proposed answer links this to computation, specifically a resource-bounded version of Kolmogorov sophistication.
Yeah, the idea that true complexity or complextropy isn't just about the shortest description in principle, but about the shortest efficient description of the underlying structure, where the specific state is still hard to pin down efficiently.
Leading to this potential first law of complexodynamics, low, high, low.
A really provocative and stimulating idea.
Absolutely. And it highlights these amazing connections between physics, information theory, computation, thermodynamics. It's all tangled together.
And it's clearly not solved yet. Lots of open questions, ongoing research, both theoretical and now empirical. It's a living field.
Which is the most exciting kind. It really makes you wonder, though. Think about other things in the world.
Like what?
I don't know, the way life evolves, the way ideas spread. Maybe even like the plot of a good story. Does interestingness follow that same arc?
That's a fascinating thought. Could this concept of resource-bounded complextropy apply more broadly than just physics?
Maybe. What kinds of systems would obey this kind of law? And what does that tell us about information and how the universe processes it? Definitely something to chew on.